So we have a couple of examples that we can do to showcase how to work with areas below the curve. The first one here, we're going to determine the area between the functions y equals x and the function y equals x squared minus 2. We can see the area showcase here, and if you look at the particular graph, we can see even one of the points where we can get the intersection. So we can talk about in those numbers intersecting in 2, but of course we don't know this point yet. So the best thing that we can do to figure out what are the intersection points and determine the interval of integration is just to set up the equations to be equals to each other. So x equals x squared minus 2. And so we're going to get a quadratic functions out of this. We get x squared minus x minus 2. We can factor this out clearly as x minus 2, x plus 1. And so from here, we're going to find out that the numbers are x equals 2 and x equals minus 1. So this point here is going to be a minus 1. Now, with that given, we're almost done with the important parts for the calculation of the area, since the area below the curve is the integration from minus 1 to 2, the function that is in top, which in this case is the line, x, minus the function that is in the bottom, which in this case is x squared minus 2. We got to be careful to put this in parentheses. So we get dx. Now the setup is complete. The next part is only using fundamental calculus theorem. And so this is going to be x squared over 2 minus x cubed over 3 plus 2x. This is the integration of this between minus 1 and 2. And of course, we plug in 2 and then we plug in 1. So we get 4 over 2 minus a over 3 plus 4 minus, and then we plug in minus 1. We have 1/2 minus minus 1 cubed is going to be minus 1. So we get a plus here, 1 over 2 and minus 2 over here. So at this point, we're almost done. Now 4 divided by 2 is 2, and 2 with minus 2 is just going to go away. And then we have things in terms of 1/3, so we can leave this 4 alone. This minus 8/3 plus 1/3 can be written as minus 7 over 3, and this minus 1/2 here. Now we can write this as 12 over 3, this 4, minus 7 over 3. And then I can transform this into 6, so I can find a common value later. And once that we have that, we have 5 over 3 minus 3 over 6. Or we can see this as 10 over 6 minus 3 over 6, and this is going to be 7 over 6. So we find out what is the area below the curve in that scenario. Now let's transition to the function y equals minus x squared plus 4x and y equals x squared minus 2x. So if we take the area between those two curves, is going to be the area between those two curves is going to be represented by the black area that we have right here. And from below, we can see the points where we're going to get the intersection. Turns out that if minus x squared plus 4x is equals to x squared minus 2x, we can write that as 2x squared minus 6x, and that's going to give us 2 points of intersection, one in x equals 0, the other one in x equals 3. Clearly, the one that is opening down has the negative x squared, and the one that opens above has the positive x squared. So we can know which of the two functions is up and down, and we know that the area is given by the integral from 0 to 3 of the top function, which is minus x squared plus 4x, minus the bottom function, which is x squared minus 2x. Now at this point, we can simplify a bit, and this is going to be minus 2x squared and plus 6x dx from 0 to 3. And if we calculate the area on here, we're going to get that this is minus 2x cubed over 3 plus 6x squared over 2 between 0 and 3. By fundamental calculus theorem, we'll plug in 3, we plug in 0. Plugging in 3 is going to be the only thing that is going to produce something non-zero. So we just plug in 3 over here. And this is going to give us the total result of the area. This is going to be minus 2 by 9, as I can cancel one of the 3's over here. And this is going to be 9 by 3, which is going to be 27. So it's 27 minus 18, and the total area is going to be 9. Now moving on to another area, we can have y equals cosine and y equals minus cosine. And let's see the area between those two curves. Now, the first thing that we can do is we can just only talk about one of the intersections. So this area in black is going to be cut for certain points. So we can say, well, when this cosine of x equals to minus cosine of x, and that's going to turn out to be when 2 cosine of x is equals 0. Or where cosine of x is equal 0. And of course, we can find those specific points for the negative value and the positive value. So this is going to be minus pi half, and this is going to be pi half over here. So the total area is calculated as the integral from minus pi half to pi half of cosine of x minus cosine of x. Notice that cosine of x is the one on top and minus cosine of x is the one on the bottom. You can verify that because when you are in 0, cosine of 0 gives you 1, and therefore minus cosine of 0 is going to give you minus 1. Once that you have set up the area, you have that this is just the integral from minus pi half to pi half of twice cosine of x dx. There's a lot of symmetry on this particular integral, so you can use either symmetry property. Notice that this is just going to be twice the area from 0 to pi half. So you can use twice that, and it's going to be 4 times the integral of cosine of x dx. At this point, the antiderivative of cosine is well known in its sign. So this is going to be 4 sine of x between 0 and pi half. And because the sine of x in 0 is 0, is only going to be 4 sine of pi half, which is going to lead to be 4. So the total area on this is going to be 4 units. Now I've done a lot of examples of doing the integration in terms of x, and certainly the next example is something that I can do in terms of x, but also I will do in terms of y. So notice this function, y equals x squared and y equals square root of x. This is going to intercept clearly when x is equals 1, since it's the only point after x equals 0 where those two functions can be intersected. The function on the top is going to be the square root of x. The function on the bottom over here is going to be the x squared. That's only happening between the interval 0 to 1. So a, or the area, is the integral from 0 to 1 of the square root of x minus x squared dx. And so we can compute really quick this here. This is just x to the 3 half over 2 thirds minus x cubed over 3 between 0 and 1. And this is just 2/3 minus 1/3. And so that's going to produce 1/3. That is if I do this type of functions in terms of x. Notice that I can also do in terms of y. And in terms of y equals x, y equals x squared is going to transform to x equals the square root of y. And the function y equals the square root of x is going to transform to y equals x squared. And so now you can see that this is y equals x squared. And now this is just the top part of x equals square root of y. And the area is going to be given by a similar situation. But now the functions are going to flip around. And I'm actually going to have this function to go first. So I'm gonna have a square root of y go first, and then minus y squared, which is going to be given by this function. Notice I'm now doing the top and bottom in this direction. So this is top, this is bottom, and so this function is the square root of y. This function is y squared. So this is going to be the y, and of course now we're going from 0 to 1 in terms of y. Notice that this is exactly the same integral, so the result is going to be exactly the same. However, you're going to find out examples of functions where it's going to be easier to have this transition in terms of y, so you don't have more than one region. That as the example presented in part 1. All right, so those are the examples and the conclusion of section 6.2.